Hi! In this video, we will cover basic approaches to feature pre-processing and feature generation for numeric features. We will understand how model choice impacts feature pre-processing, we will identify the pre-processing methods that are used most often, and we will discuss feature generation and go through several examples. Let's start with pre-processing. First thing you need to know about handling numeric features is that there are models which do and don't depend on feature scale. For now, we will broadly divide all models into tree-based models and non-tree-based models. For example, decision trees classifier tries to find the most useful split for each feature, and it won't change its behavior and its predictions if we multiply the feature by a constant and retrain the model. On the other side, there are models which depend on this kind of transformations, the model based on nearest neighbors, linear models, and neural network. Let's consider the following example. We have a binary classification task with two features. The objects in the picture belong to different classes, the red circle to class 0 and the blue cross to class 1. And finally, the class of the green object is unknown. Here we will use a one nearest neighbors model to predict the class of the green object. We will measure distance using square distance, which is also called L2 metric. Now, if we calculate distances to the red circle and to the blue cross, we will see that our model will predict class 1 for the green object, because the blue cross of class 1 is much closer than the red circle. But if we multiply the first feature by 10, the red circle will become the closest object, and we will get an opposite prediction. Let's now consider two extreme cases. What will happen if we multiply the first feature by 0 and by 1 million? If the feature is multiplied by 0, then every object will have the feature value of 0, resulting in KNN ignoring that feature. On the opposite, if the feature is multiplied by 1 million, slightest differences in that feature's values will impact prediction, and this will result in KNN favoring that feature over all others. Great! But what about other models? Linear models are also experiencing difficulties with differently scaled features. First, we want regularization to be applied to linear models' coefficients for features in equal amount, but in fact, regularization impact turns out to be proportional to feature scale. And second, gradient descent methods can go crazy without a proper scaling. Due to the same reasons, neural networks are similar to linear models in requirements for feature pre-processing. It is important to understand that different feature scalings result in different models' quality. In this sense, it is just another hyperparameter you need to optimize. The easiest way to do this is to rescale all features to the same scale, for example, to make the minimum of a feature equal to 0 and the maximum equal to 1. We can achieve this in two steps. First, we subtract minimum value, and second, we divide the difference by its maximum. It can be done with min-max scaler from sklearn. Let's illustrate this with an example. We apply so-called min-max scaler to two features from the Titanic dataset, age and CBSP. Looking at histograms, we see that the features have different scale. Age is between 0 and 80, while CBSP is between 0 and 8. Let's apply min-max scaling and see what it will do. Indeed, we see that after this transformation, both age and CBSP features were successfully converted to the same value range of 0–1. Note that distributions of values which we observe from the histograms didn't change. To give you another example, we can apply a scaler named standard scaler in sklearn, which basically first subtract mean value from the feature and then divides the result by feature standard deviation. This way we get standardized distribution with mean of 0 and standard deviation of 1. After either of min-max scaling or standard scaling transformations, features' impacts on non-tree-based models will be roughly similar. Even more, if we want to use KNN, we can go one step ahead and recall that the bigger feature is, the more important it will be for KNN. So we can optimize scaling parameter to boost features which seems to be more important for us and see if this helps. When we work with linear models, There is another important moment that influences model training results. I am talking about outliers. For example, in this plot, we have one feature x and a target variable y. If we fit a simple linear model, its predictions can look just like the red line. But if we will have one outlier with x feature equal to some huge value, predictions of the linear model will look more like the purple line. The same holds not only for features values, but also for target values. For example, let's imagine we have a model trained on a data with target values between 0 and 1. Let's think what happens if we add a new sample in the training data with a target value of 1000. When we retrain the model will predict abnormally high values. Obviously, we have to fix this somehow. To protect linear models from outliers, we can clip features values between two chosen values of lower bound and upper bound. We can choose them as some percentiles of that feature, for example 1st and 99th percentiles. This procedure of clipping is well known in financial data and it is called vinsorization. Let's take a look at this histogram for an example. We see that the majority of feature values are between 0 and 400. But there is a number of outliers with values around -1000. They can make life a lot harder for our nice and simple linear model. Let's clip this feature's value range, and to do so, first we will calculate lower bound and upper bound values as features values at 1st and 99th percentiles. After we clip the features values, we can see that features distribution looks fine, and we hope now this feature will be more useful for our model. Another effective pre-processing for numeric features is the rank transformation. Basically, it sets spaces between properly sorted values to be equal. This transformation, for example, can be a better option than min-max scalar if we have outliers, because rank transformation will move the outliers closer to other objects. Let's understand rank using this example. If we apply rank to the sorted array, it will just change values to their indices. Now, if we apply rank to the not sorted array, it will sort this array, define mapping between values and indices in the sorted array, and apply this mapping to the initial array. Linear models, KNN, and neural networks can benefit from this kind of transformation if we have no time to handle outliers manually. Rank can be imported as a rank data function from SciPy. One more important note about the rank transformation is that to apply it to the test data, you need to store the created mapping from features values to their rank values. Or alternatively, you can concatenate, train and test data before applying the rank transformation. There is one more example of numeric features pre-processing which often helps non-tree-based models, and especially neural networks. You can apply log transformation to your data, or, as another possibility, you can extract x-square root of the data. Both these transformations can be useful because they drive two big values closer to the feature's average value. Along with this, the values near 0 are becoming a bit more distinguishable. Despite the simplicity, one of these transformations can improve your neural network's results significantly. Another important moment which holds true for all pre-processings is that sometimes it is beneficial to train a model on concatenated data frames produced by different pre-processings, or to mixed models trained on differently pre-processed data. Again, linear models, KNN, and neural networks can benefit hugely from this. To this end, we have discussed numeric feature pre-processing, how model choice impacts feature pre-processing, and what are the most commonly used pre-processing methods. Let's now move on to feature generation. Feature generation is a process of creating new features using knowledge about the features and the task. It helps us by making model training more simple and effective. Sometimes we can engineer these features using prior knowledge and logic. Sometimes we have to dig into the data, create and check hypotheses, and use this derived knowledge and our intuition to derive new features. Here we will discuss feature generation with prior knowledge, but as it turns out, an ability to dig into the data and derive insights is what makes a good competitor a great one. We will thoroughly analyze and illustrate this skill in the next lessons on exploratory data analysis. For now, let's discuss examples of feature generation for numeric features. First, let's start with a simple one. If we have columns real estate price and real estate squared area in the dataset, we can quickly add one more feature, price per meter squared. Easy, and this seems quite reasonable. Or let me give you another quick example from the forest cover type prediction dataset. If we have a horizontal distance to water source and the vertical difference in height between the point and the water source, we as well may add combined feature indicating the direct distance to the water from this point. Among other things, it is useful to know that adding multiplications, divisions and other features interactions can be of help not only for linear models. For example, although gradient boosting decision tree is a very powerful model, it still experiences difficulties with approximation of multiplications and divisions, and adding such features explicitly can lead to a more robust model with less amount of trees. The third example of feature generation for numeric features is also very interesting. Sometimes, if we have prices of products as a feature, we can add new feature indicating fractional part of these prices. For example, if some product costs 2.49, the fractional part of its price is 0.49. This feature can help the model utilize the differences in people's perception of these prices. Also, we can find similar patterns in tasks which require distinguishing between a human and a robot. For example, if we will have some kind of financial data like auctions, we could observe that people tend to set round numbers as prices and never something like 0.935 blah blah blah, very long number here. Or, if we are trying to find spam bots on social networks, we can be sure that no human ever writes messages with an exact interval of 1 second. Great! These three examples should have provided you an idea that creativity and data understanding are the keys to productive feature generation. Alright, let's summarize this all. In this video, we have discussed numeric features. First, the impact of feature pre-processing is different for different models. Tree-based models don't depend on scaling, while non-tree-based models hugely depend on it. Second, we can treat scaling as an important hyperparameter in cases when the choice of scaling impacts predictions quality. And at last, we should remember that feature generation is powered by an understanding of the data. Remember this lesson, and this knowledge will surely help you in your next competition.